Hello everyone. We usually think of graphene as the ultimate 2D material, a perfectly flat sheet of carbon, just one atom thick. But today, we're going to look at it from a different dimension. We're going to explore a 3D version of graphene, and more importantly, we'll see why scientists deliberately break its perfect structure to create something called graphene oxide. It might sound counterintuitive to ruin a flawless material, but as you'll see, this intentional damage is exactly what makes it useful for the real world. Imagine taking flat sheets of graphene, curling them into spheres, and nesting them inside one another, much like a Russian nesting doll. This is what we call onion-like graphene, or carbon nano-onions. Why do we want this shape? Unlike a flat sheet, a sphere has no sharp, reactive edges. These carbon spheres are highly stable, have a massive surface area, and conduct electricity beautifully. In practice, this makes them perfect for nanoscale lubricants. Think of them as microscopic ball bearings that drop friction in mechanical systems almost to zero. They are also incredibly promising for supercapacitors, energy storage devices that could one day charge your electronics in a matter of seconds. But here is the catch. Pure carbon is chemically inert. Its atoms are locked into such a perfect, stable lattice that there are simply no loose ends or active spots left to react with anything else. Because of this closed-off nature, it is naturally hydrophobic. It repels water and is notoriously stubborn when it comes to mixing. While scientists can coax these nanospheres into a liquid dispersion using special additives like surfactants, on their own, they just want to clump together and settle at the bottom. To make them truly versatile and easy to use in complex technologies, we need a more permanent solution. We do this through a process called functionalization. We chemically bond oxygen atoms to the smooth carbon surface, turning it into graphene oxide. Why oxygen? Because we need to create chemical anchors on that slippery carbon surface. Think of them as molecular Velcro, specific spots where other molecules can finally grab on. How is this actually done? While there are several different methods to synthesize graphene oxide, they all share one core principle. You have to break the perfect carbon lattice. The carbon-to-carbon bonds in pure graphene are incredibly strong, leaving no room for anything else to attach. To functionalize it, scientists use harsh oxidizing environments to intentionally snap some of those bonds. This process essentially cracks open tiny parts of the flawless carbon armor, creating highly reactive gaps. Once the lattice is breached, oxygen atoms can permanently embed themselves into the structure. Once the reaction is done, our graphene spheres are covered in what chemists call functional groups. There are three main players here. First, we have carboxyl groups. These usually attach to the edges or the damaged spots, acting as very strong chemical anchors. Then, spread across the rest of the sphere, we have hydroxyl and epoxy groups. It is true, the perfect, beautiful symmetry of pure graphene is gone. But in exchange, we get a material with completely new, highly adjustable properties. Let's look at what this new graphene oxide can actually do. First, it loves water. It goes from being completely hydrophobic to hydrophilic. Instead of clumping up, it forms stable, smooth mixtures in liquids. Second, it becomes highly reactive. Thanks to those oxygen anchors, we can now bind it to almost anything: polymers, proteins, or metal ions. Third, its electrical conductivity becomes completely tunable. Adding oxygen initially turns the material into an electrical insulator. However, the process isn't just all or nothing. By carefully controlling the exact number of these functional groups on the surface, scientists can dial the electrical conductivity up or down. It acts like a molecular dimmer switch, letting us tune the material to the exact level a specific technology requires. And fourth, it acts like a microscopic rebar. When mixed into other materials, it grips them tightly, creating incredibly strong composites. So where does all this lead us? The applications are staggering. In biomedicine, these spheres make perfect delivery vehicles. Because they are stable and covered in chemical hooks, we can attach medication to them and send them directly to cancer cells, leaving healthy tissue untouched. In environmental science, graphene oxide acts as an ultra-fine molecular sponge, capable of pulling heavy metals and toxins straight out of contaminated water. In material science, adding just a tiny fraction of a percent to plastics, rubber, or concrete can multiply their strength and heat resistance. As you can see, sometimes you have to break something perfect to make it truly useful. By adding oxygen to graphene, we take an isolated wonder material and turn it into a highly versatile tool for engineering and medicine. Today, we've just scratched the surface. In our upcoming videos, we will dive deeper and talk in more detail about the specific fields and industries where graphene oxide is most useful. Subscribe to the channel, leave your questions in the comments, and I'll see you next time.